Good day. Today we are going to discuss Part 7 of Module 6 for the subject CE 3151, Fitting Curves and Interpolation. In this lecture, we are going to discuss the second method for polynomial interpolation, which is the backward Gregory-Newton. The backward Gregory-Newton is another approximation that uses regular x interval. The required function of x would now fall on the second half of the data points, unlike for the forward Gregory-Newton method. The closest approximation for the function of x would now be taken from the backward leading differences. An alternative for the solution is to use the value of the succeeding required but is limited to when the difference table closes to 0. If the table does not end in 0, then we use the value of x sub n of the given data set. The conditions for backward Gregory-Newton method would be somewhat similar to that of the forward Gregory-Newton, wherein the intervals of x would be of equal value. That is, for each value of x would be equal to each other. The difference is that for forward Gregory-Newton, the value of the function of x is found before the midline of the given data set, while for backward Gregory-Newton, the function of x would be found after the middle line or the midline of the given data set. The formula for the interpolation of backward Gregory-Newton would be similar to that of forward Gregory-Newton method. That is, the function of x is identical to the function of x sub o plus r sub h, wherein this equation would now be written as y sub n plus r times nabla y sub n plus r times r plus 1 all over 2 factorial times nabla squared y sub n plus r times r plus 1 plus r times r plus 1, 2 all over 3 factorial times delta cube y sub n. So there are some similarities and a difference, a very visible difference between backward and the forward Gregory-Newton. That is, for r of backward Gregory-Newton, that will now be computed as x minus x sub n all over h, wherein for the forward Gregory-Newton, instead of using x sub n, we use the first value of the given x in the dataset. Likewise, for r plus 1, in forward Gregory-Newton, we have the sign as subtraction or minus, r minus 1. So, to remember the difference between forward and backward, for forward Gregory-Newton, for r, we use the first value of x, and we use r minus 1, r minus 2. Unlike for backwards, we use the last value of x in the dataset, and we use addition for our terms for each succeeding term. So take note that for y sub n, nabla sub y sub n, nabla squared y sub n, and nabla cube y sub n would be our leading backward differences, which are taken from the table of finite differences. So to understand backward Gregory-Newton, let's solve an example. For the given data set, determine the function of x for x equal to 10.5. So again, we determine first our leading backward differences, whereas nabla y sub n is now equal to negative 22 minus negative 4, which is 18. Negative 4 and 19 would give 23. 47 minus 19 is 20. Then we solve for nabla squared y sub n, which gives us 5 and 5. And nabla cube y sub n would give us 0. So from here, we can now solve or determine our lead backward differences, which is 47, 28, 5, and 0. Next, we solve for the value of h for all values of x, and that's equal to 3. So solving now for r, it's equal to x minus x sub n all over h, wherein x is 10.5, and x sub n is equal to 12. Divide it by 3, we get now a value of 0.5 negative. Substituting the value of r and the values of y and nabla y in our equation for function of x, we get 47 plus negative 0.5 times 28 plus negative 0.5 times negative 0.5 plus 1 all over 2 factorial times 5 is 0, which gives us the value of the function of x equal to 10.5 as 32.375. So if we're going to look at our value, 10.5 is between 9 and 12, and the function of x, which is equal to y, is 32.375, which is also between the value of 19 and 47. Another example for backward Gregory Newton. Determine the function of x for x equal to 6.5 for the given data set. So again, we start off first with our finite difference table. So we solve for nabla y sub n. So we have negative 3 minus negative 7 is 4. 6 minus negative 3 is 9. 25 minus 6, 19. 62 minus 25, 37. 129 minus 62 is 67. Next, we move on to nabla squared y sub n. So we have 9 minus 4 is 5. 19 minus 9 is 10. 37 minus 19 is 18. 67 minus 37 is 30. So followed by nabla cube y sub n, we get 5, 8, and 12. Nabla raised to 4 y sub n, so we get 3 and 4. And lastly, we have nabla raised to 5 y sub n, giving us 1. So from this table, we have closed it already, and we are able to identify now our leading backward difference with 129, 67, 30, 12, 4, and 1 for the values of y sub o and the values of nablas. So next, we determine the value of each for x intervals that is now equal to 1. R is computed as x minus x sub n all over h. So x is 6.5, and our last value of x is negative 7. So divide this by h, we get r equal to negative 0.5. So for the function of x equal to y sub n plus r, nabla y sub n, plus r times r plus 1 all over 2 factorial times nabla squared y sub n, and so on. So substituting the values of r and our leading backward difference, we get function of x is equal to 129 plus negative 0.5 times 67 plus 0.5 negative times negative 0.5 plus 1 all over 2 factorial times 30 plus negative 0.5 times negative 0.5 plus 1 times negative 0.5 plus 2 all over 3 factorial times 12, negative 0.5 times negative 0.5 plus 1 times negative 0.5 plus 2 times negative 0.5 plus 3 all over 4 factorial times 4 plus negative 0.5 times the quantity negative 0.5 plus 1 multiplied to the quantity negative 0.5 plus 2 times the quantity negative 0.5 plus 3 times negative 0.5 plus 4 all over 5 factorial times 1. Simplifying this, we have the function of 6.5 is equal to 129 minus 33.53 plus 0.75 minus 0.5625 plus 0.027, 34375, or that is now equivalent to 92.37, 109,375. Example number 3 for backward Gregory Newton. For the given data set, we solve the function of x for x equal to 4.25. So again, we have our finite difference table. So we solve first for nabla y sub n. So we have 83 minus 15, 68. 519 minus 83, we get 436. 1,659 minus 518 is 1,140. 3,839 minus 1,659 is 2,180. 5,395 minus 3,839 is 3,556. So next we have nabla squared y sub n. We have 368, 704, 1,040, and 1,376. For nabla cube y sub n, we have 336, 336, 336, thus closing at nabla raised to 4 y sub n at values of 0 and 0. So we have our leading backward differences at 7395, 3556, 1376, 336, and 0. So from there, we can compute now for each as equal to 1. So based now on our last point on the given data set, that is x sub n equal to 6. So we can now solve for your r as x minus x sub n all over h. That is 4.25 minus 6 all over 1, giving us a value of r equal to negative 1.75. So we substitute r and our values for y and nabla y sub n in the equation. We have now function of x is equal to 7395 plus negative 1.75 times 3556 plus negative 1.75 times the quantity negative 1.75 plus 1 all over 2 factorial times 1,376 plus negative 1.75 times the quantity negative 1.75 plus 1 times negative 1.75 plus 2 all over 3 factorial times 336 plus 0. Simplifying this, we have the function of x equal to 4.25 is equal to 7395 minus 6223 plus 903 plus 19375, or that's equal to 2093.375. Another way of solving example number 3 is by the value based on the point after the required x. So since our value of x is 4.25 and it is after the value 4, therefore, for our solution, we are going to use now x sub n equal to the point after our required, which is 5. So with that, we can now solve for r is equal to x 4.25 minus x sub n minus 5 all over h equal to 1, thus giving us a value of negative 0.75. So using our computed finite difference table, we will now be using the backward differences at 5, that is now 3839, 2180, 1040, 336, and 0. So for our computation, we will now be substituting the values of r and our backward differences as highlighted in the function of x equation. So we get the function of x is equal to 3839 plus negative 0.75 times 2180 plus negative 0.75 times the quantity negative 0.75 plus 1 over 2 factorial times 1040 plus negative 0.75 times negative 0.75 plus 1 times the quantity negative 0.75 plus 2 all over 3 factorial times 336 plus 0. Simplifying, the function of x equal to 4.25 is equal to 3839 minus 1635 minus 97.5 minus 13.125, which will give us a value of 2093.375, which is exactly the same as our previous solution. Again, proving that this solution is only applied or can be applied if our table closes at a value of 0. So another example for backward Gregory Newton is for the given data set, we compute for the function of x for x equal to 2.0. So again, we complete our finite difference table with nabla y sum in. So we have 7.1 minus 5.1 is equal to 2. 8 minus 7.1 is 0.9. 8.1 minus 8 is 0.1. 7.8 minus 8.1 gives us negative 0.3. Nabla squared y sum n will give us negative 1.1, negative 0.8, and negative 0.4. Nabla cube y sum n gives us 0.3 and 0.4. And closing our table, we have nabla raised to 4 y sum n 0.1. So we solve now or have identified our leading backward differences with quantities 7.8, negative 0.3, negative 0.4, 0.4, and 0.1. So for our h, that is computed 0.6 as the interval for all values of x. For our r, we compute this as x minus x sub n over h, and that is now equal to 2 minus 2.8 divided by 0.6, giving us a value of negative 4 over 3. In this case, we are basing our computation of r on the last point of our data set, wherein x n is equal to 2.8 with an equivalent y sub o of 7 or y sub n of 7.8. So substituting the value of r and our values of y and nabla y, we get f of x is equal to 7.8 plus negative 4 over 3 times negative 0.3 plus negative 4 over 3 times negative 4 over 3 plus 1 times negative 0.4 plus negative 4 over 3 times negative 4.3 plus 1 times negative 4 over 3 plus 2 over 3 factorial times 0.4 plus negative 4 over 3 times negative 4 over 3 plus 1 times negative 4 over 3 plus 2 times negative 4 over 3 plus 3 all over 4 factorial times 0.1, giving us a value of the function x equal to 2 is equal to 7.8 plus 0.4 minus 0.889 plus 0.0197 plus 0.002058, which is a total of 7.332918. So if you're going to solve example number 4 using the point after the required x2, which is found after 1.6, so the point after 2 is the point 2.2. So therefore, we're going to use now x sub n equal to 2.2 in our computation of r. So for r, that will now be x minus x sub n all over h, or that's 2 minus 2.2 all over 0.6, giving us a value of negative 1 all over 3. Using our computed finite difference table, so we are going to use that value of the differences at x equal to 2.2. So we'll have values of 8.1, 0.1 at negative 0.8, and 0.3 for our equations. So substituting the value of r and our y and nabla y sub n, so we'll have f of x is equal to 8.1 times negative 1 over 3 times 0.1 plus negative 1 over 3 times negative 1 over 3 plus 1 all over 2 factorial times negative 0.8 plus negative 1 over 3 times negative 1 over 3 plus 1 times negative 1 over 3 plus 2 all over 3 factorial times 0.3. So solving this, we get a value of the function of x equal to 2 as 7.8370, which is not equal to our previously solved value, which is 7.33291. So again, proving that our solution, or we can use the value of x sub n, or the point after the required x, only if we are closing our finite table with a value of 0. That's it for backward Gregory Newton method. Thank you for listening.